Hello there. Welcome to Astraveo's continuing education series, where for our podcast listeners, we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going. Good evening, and welcome back to Astraveo's continuing education series. We've been off the air for a little while. We've been attending to our families and doing our day jobs and doing a little bit of scientific research and writing our science papers. So we haven't been able to get to a video for a wee while, but we wanted to do a little bit of an exciting topic or two during the summer season while all the kids are off school, and of course taking them to the beach, and Joseph's walking his dog, and we're doing all kinds of exciting things. But tonight we're going to talk about one of my favourite subjects in astronomy and physics. And yes, I know I say this almost every video. I've always got my favourites, but this is a real fundamental, and it sort of governs everything we know really about the observable universe, our lives. Of course, we get heat and energy from the sun, and of course, I'm talking about radiation. Now, radiation is really, really interesting. It's been studied for an awful long time, but only in the last century, really, last 100 years or so, have we really started to understand it in depth. And of course, we can thank Madame Curie, Dr. Curie, for this, where she made a wonderful breakthrough in understanding the origins of radiation with her work with radium, which she won 2 Nobel Prizes. Very exciting. So we're going to talk about the fundamentals of radiation. Now, there are 4 main processes or manifestations of radiation that we can talk about, and I'm going to list them. And an eagle-eyed viewer told me that my writing on the whiteboard sometimes is a little bit small, so I'm going to try to be a little bit better, a little bit more focused on writing a little bit bigger, a little bit clearer. Okay, so radiation. Okay, I'm just going to give ourselves a really big subject here. Radiation. Okay, now the first is alpha particles. Now, alpha is the first letter of the Greek alphabet, so alpha. Number 2 is beta particles, or beta rays, sometimes they're called. Whoops, I did say it right nicely, and I already made a mistake. Particles. And again, beta is the second letter of the Greek alphabet. Whoops. Beta. Number 3 is, as you may be able to guess, not starting off great tonight, gamma rays. And of course, gamma is the third letter of the Greek alphabet, gamma. And then number 4, and I am going to include it, but I'm going to include it way, way, way off here, is neutrons. Now, neutrons is a funky one. They're not, for a long time, wasn't typically considered a form of radiation, but it is, neutrons can be given off by atoms, and so that we really should cover that. Okay, well, I'll tell you what we'll do. We're going to write them out here again so that we can explain them one by one. Okay, so number 1, alpha particles, squeaky pen syndrome, I've missed you. Number 2, beta particles. Number 3 are gamma rays. And number 4 are neutrons. Now, I did say that these are the 4 main processes for radiation. And typically what I mean by this is radioactive decay. The lights here, the what looks like LED strips here, that's a form of radiation. Light from the sun is a form of radiation. These are photons. Now, one of these forms of radiation here are photons as well. Yes, it's gamma rays. But by these really what we're talking about here are from radiometric decay. So really it's the decay of the inside of an atom, basically at the nucleus level. So radiation, I'm not touching on X-rays, for instance, or radio waves, or the infrared, or the visible that we humans and most animals see in the world around us. I'm specifically talking about radiometric decay of atoms. Okay, so let's just give ourselves some space, as we always do, the famous astronomy saying, of course. Okay, I'm going to get rid of that, just so we know we're talking about radiation. Well, we need to know some fundamentals about atomic physics or atomic chemistry to understand what's going on here. So let's draw ourselves the most simple element, which of course is hydrogen. Now, hydrogen, the chemical symbol is H, as you might imagine. Okay, so it's H like this, H, and it is written 1, 1. Now what that means is, it's the lower number is the number of protons in the element, which is 1. And then the mass number is also 1, because there is only 1 proton. So for instance, here, a hydrogen atom looks like a proton in the middle, with an electron, but not drawn to size, of course, orbiting it. It's electrically neutral because you have 1 electron with a minus charge and 1 proton in the middle of the nucleus, in the middle of the atom essentially, with a positive charge. Negative and positive balance out. Now in terms of mass, they're not balanced out. The mass of a proton is way, way heavier and more massive than an electron. There are about, if I remember my atomic physics correctly, 1,837 electron masses in a proton. So the mass isn't balanced, the charges are balanced, and this is a neutral atom of hydrogen. Well, many elements, not all of them, but many of them can come in isotopes, different flavors. Now, an isotope is an element that has the same number of protons. That's almost by definition, actually. If you have a different number of protons, you're a different element. But they have different number of neutrons. And now that's important because many isotopes of elements are unstable. And that leads to radiometric decay, radioactive decay. So what do we know about the isotopes of hydrogen? Let's keep it simple. Well, there are 2 isotopes, or 3 in total, actually. We have 1, 1 hydrogen. We have 2, 1 hydrogen. And I'm going to give myself a wee bit of space. We have 3, 1 hydrogen. Now, the atomic number stays the same. There's 1 proton. It has to. That's the definition of an element. It's the number of protons there are in the nucleus. Hydrogen, of course, has 1. However, what happens here is you have a proton orbited by an electron. This is the hydrogen we know about in everyday life. Hydrogen. Perfect. 2, 1. Now, there's something changed here. We've gone from 1 to 2. This is the mass number. This is the total number of mass that you have in the nucleus. Now it's 2, that means there are 2 particles there. And in fact, there is a proton and a neutron now. So 1 proton, there's the atomic number here, the mass number up here because there are 2 of them. And the neutron and the proton, the masses are almost identical, not quite, but almost. And so this would be the nucleus. Don't forget, its charge is still just 1 proton, it's just 1 positive. The neutron is electrically neutral, so it's still just a charge of +1, and it has 1 electron orbiting it, so it's electrically neutral. This isotope is called deuterium. Deuterium. Okay, now this is fundamental. It's a fundamental isotope when we start talking about radioactive decay, radioactive, unfortunately, atomic bombs, and in a perfect world, it would be for power generation. Now, this one, as you might have seen in a couple of films, like the Spider-Man one with the Octavia Sky, where they're trying to make the sustainable fusion reactor, they use tritium. Now, tritium, 3, so we've now got 3 particles, and in fact, it's a proton, a neutron, and a neutron. In the nucleus, it's still just 1 positive because there's only 1 proton. These 2 are electrically neutral. But there are now 3 particles in the nucleus. So its mass number is 3, but its atomic number is still 1 because there's just 1 proton. 1 electron orbiting it, it's electrically stable. So we have hydrogen, deuterium, and tritium. They're all identical in many ways, except, okay, so let's do the identical part first. 1 proton, 1 proton, 1 proton. Same element, hydrogen. 1 electron, 1 electron, 1 electron. It's electrically neutral. Negative charge of an electron matches the positive charge of a proton. However, with the isotopes, with deuterium, you get an extra neutron. With tritium, you get 2 extra neutrons. So what do you think is the common factor here? Yes, the proton. Yes, the electron, they're electrically neutral. However, these two isotopes are not stable. And they're not stable because the nucleus is sort of juggling as what's going on here. The proton and the neutron are sort of trying to get stable. And there are energy levels inside the nucleus, and so sometimes there's a sort of balance of how they become stable. The same here with tritium. Again, you have two neutrons, one proton. Things aren't quite stable. The proton is sort of jostling for position in the nucleus to try and always be with the right electrical charge and electrical attraction with the electron. Now, what that means is if these two are not stable, they try to become stable because everything in the universe tries to get to its lowest energy state because that's where it's comfortable. If I drop this pen, its lowest energy state is on the floor. It's going to turn its gravitational potential energy into kinetic, and it will end up at a lower potential. It's trying to minimize its energy state. Well, atoms do the same thing, and they do it by releasing radiation, radioactive decay. So this is important. So this is really how you get these different forms of radiation, radiometric radiation, is by typically it's the nucleus trying to become more stable. It's when isotopes are unstable, they emit radiation in these forms to try to become more stable. So let's talk it through. Those are isotopes. Okay, hydrogen, deuterium, tritium. Very nice. Okay, let's give ourselves some space because we, as I am fond of saying in these videos, are in business now. So let's start with one of the most simple forms, alpha particles. Now, alpha particles are quite simple. They are essentially, let's just write it out. And again, I'm going to try and use big writing because a couple of people have told me my writing's not big enough and it's hard to read. Now, an alpha particle, essentially, it's a bit of an interesting one. It's a proton, and a neutron, and a neutron. I'm going to give them little circles because they're fundamental particles here. So basically, this is one particle there sort of attached. Now you'll notice I haven't drawn any electrons around this. So this has a charge, this particle has a charge of plus 2 plus. There are two protons. Neutrons are electrically neutral, remember. Now, these particles can be quite dangerous. They can ionize matter and they can cause real damage to humans. Now, they tend to be fairly slowly moving. As you can tell, they're made up of nucleus-like material, protons and neutrons. So some unstable isotope of, I don't know what, it could be something like lead or argon or krypton, something like that, could be trying to become stable. And so it will emit an alpha particle. And it's made up of two protons and two neutrons. Now, the strong nuclear force is keeping those together. They don't go off in their own way. Positive charge of 2. Now, they're quite big, they're quite massive because there are 4 particles, quite charged. However, they move quite slowly. So they don't cause that much damage unless you're really close to them. They don't travel very far in air. Oh, squeaky pen. You're talking maybe a couple of centimeters, I don't know, let's say 3-4 centimeters. So alpha particles tend to move maybe this far before they interact with air. Now that would be the same at the table in front of me, the board here, us, humans, life. Now they can be quite damaging because they're very highly charged, +2, and they're quite massive. There are 4 particles. And so even though they move relatively slowly, they can do quite a lot of cellular damage. So in fact, that's one of the ways that if there were a nuclear event, that would be one major way we would get, it'd be critical to human life, is these alpha particles. Even though they only go a small distance in air, they're quite damaging to biological cells because they carry quite a lot of mass and they have charge. They can cause ionization, which cause cellular damage. Now, if you had, I'm really bad at drawing, I think you all know this by now, a piece of paper, that's probably enough to stop alpha particles, at least some of the slowest ones. And so this alpha particle would react with the paper, interact with the paper because it's quite massive, 2 protons, 2 neutrons, and be blocked, be attenuated. So if there were an alpha source, an alpha radiation source, alpha particle source at the other end of the room, say a lump of radium or something like that, I'd be safe here. If it was 10 meters away, I'd be perfectly safe. 1 or 2 particles may occasionally get through. They just may have the right momentum to sort of not interact with the air in this room. But the vast majority of them are going to be interacting with other particles in the air I'll be safe. Now, the eagle eyes among you, and I know my young friend Jasper over there in Hawaii, one of the family friends I have out there, his wonderful mother Julia. She was in my Juliana was in my astronomy class when I was teaching out there. Very, very creative lady, an artist, very, very good at astronomy, understood concepts really well by drawing them. Well, she's got two wonderful children, and Jasper, the eldest, is very, very good scientist, very good mathematician. Now, he will recognize this, I bet, to be the nucleus, a proton and a proton, neutron and a neutron, of a helium atom. Now, we need a couple of electrons, which we don't have. So this would be, I don't know whichever the spin is, it's a cloud of spin, actually. But this nucleus, the chemical symbol for helium is He. The numbers, the atomic number is 2. There are 2 protons, and the mass number is 4 because there are 4 particles in total in the nucleus. So really, an alpha particle is just a helium nucleus without the electrons. Okay, so that's alpha particle. Quite nice. Remember, this is a nuclear process related to the nucleus. This is the ejection of a 4-particle nucleus. There are 1, 2, 3, 4, 2 protons, 2 neutrons, that's being emitted by the nucleus of a radioactive element trying, or an isotope, trying to become more stable. It's ejecting these alpha particles in an effort to make the nucleus itself more stable. That's why it's doing it. Okay, so and use my nice purple pen here. We know that these are proton, proton, neutron, neutron. Okay? Oh, squeaky pen. Quite ionizing, has a 2+ charge, quite massive, so can cause lots of damage. Okay, so let's move on to the next one, beta particles. Now these are interesting. Okay, so beta particles. Oh, I like beta particles. So I'm going to get rid of this. I'm going to cheat and leave the word particle up. Go back to my red pen. Oops. Beta particles. Now, beta particles are interesting. They are actually just electrons. Electrons. That's all they are. Now, again, they're being emitted. You have to be careful here. They're being emitted by the nucleus, not the electrons around the atom, the nucleus itself. So we said helium is proton, proton, neutron, neutron. There's the nucleus being orbited by 2 electrons. 2 positives, 2 electrons, electrically neutral. That's what a helium atom looks like. That's the nucleus with 2 electrons. These beta particles, these electrons are not the atomic electrons. They are coming from the nucleus. Are there any electrons in the nucleus there? No, sort of. You've got to be careful. Atomic physics at this level is fairly simple. But once you start getting into the real details, you can find some very, very interesting goings on. That's why we love physics so much. A neutron has a very special makeup. It's actually a proton plus an electron, and it also has a very, very weakly interacting particle. It looks like a gamma, and never really... I think that's the symbol for a neutrino. It's an antineutrino, actually. So an antineutrino is a subatomic particle, almost massless. In fact, we originally thought they were not massless, but experiments done with the sun show that they actually have very, very tiny masses. Very, very small indeed. But a neutron really is, you can think of it as a proton and an electron and this little neutrino, an antineutrino, and a little e there because it's an electron neutrino. There are a couple of different flavors. Well, electrically charged, plus, minus, this doesn't have a charge, plus and minus is neutral. So this makes sense. So now we do have a source of electrons. And so what happens is, as this nucleus is trying to become more stable, what it does and I've got a good example here, and I wrote it down just so I wouldn't forget it. We are going to take carbon, and I've got to make sure I get this right, 14.6. Carbon 6. Carbon is the element number 6. Now, its total atomic mass number is 14, which must mean it has 1, 2, 3, 4, 5, 6 protons. Oh my gosh, don't know if I've got enough space to do this, but it must have 8 neutrons. Neutron, 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 neutron. 1, 2, 3, 4, 5, 6. Neutron, neutron. And I'm not going to draw the electrons because there'll be 6 electrons orbiting this. But this is what the nucleus of a 14.6 isotope of carbon looks like. Okay, it's relatively fairly rare. It has 1, 2, 3, 4, 5, 6 protons. It must be carbon. That's the element carbon has 6 protons. It has 1, 2, 3, 4, 5, 6, 7, 8 neutrons. So its chemical symbol or atomic symbol is 14.6 carbon. This nucleus is not stable. It is dying to become more stable. And so these neutrons and protons are jostling around to try and become more stable. The protons are trying to get in their energy levels so that they are very stable. So the strong nuclear force is having all kinds of fun here. Well, how can it do that? Well, what it does, it says, look, I'm not happy here. There's something going on. I need to become more stable. And of course, we don't have consciousness that we know of, but I'm talking it through in my head to make it more human. What it does, one of these neutrons says, right, I tell you what, I am going to transform into a proton, an electron, fast moving, and an anti-electron neutrino. You have to have the anti-electron neutrino to balance the energy budget. It took us a long time to realize that, but the likes of Feynman and some very clever physicists figured this out about 80 odd years ago. I can't remember when the first neutrinos were theorized, actually. If you know, please write it in the comments below. Of course, I'll research it when I go home, but if you do know, put it in the comments. I'd love you to do your own research. So if one of these neutrons transforms into a proton, an electron, and an antineutrino, well, the antineutrino is essentially massless, has a very small mass. It's not going to interact with anything, or very, very little. It's just going to go off into the universe, into the ether, into wherever the heck, anywhere. It'd be very hard to detect, actually. Well, the proton is going to stay inside the nucleus, but this electron is going to get ejected. It's going to get ejected really quite rapidly. So what happens here is it transforms. Carbon is going to be transformed because as it emits a beta particle, this is the beta particle right here. Remember I said it's a very fast electron. There it is. But a neutron has gone. So we started with 8 neutrons. 1, 2, 3, 4, 5, 6, 7. Not 8. One of them's transformed. There were 6 protons, but now there are 7. Proton, 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 proton. 1, 2, 3, 4, 5, 6, 7. So is that still carbon? No, it's not. Because don't forget, to be the element carbon, you have to have 6 protons. 1, 2, 3, 4, 5, 6. Well, now we have 7. Well, the element with 7 protons is called nitrogen. So this carbon is transformed into 7 nitrogen. 1, 2, 3, 4, 5, 6, 7. 7 protons. But we lost an electron. We went from 8 neutrons. We lost a neutron. It went from 8 neutrons to 7 neutrons. So 7 plus 7 is 14. So while the total atomic mass stays the same, the atomic number goes up by 1. We've transformed carbon into nitrogen. And this is now stable because you have the same number of neutrons as you do protons. So this nucleus is now stable. It's where it wants to be. Now here, this carbon will have 6 electrons. So this is going to end up with an extra positive charge. So what will happen is very quickly it will find an electron to make itself electrically neutral. Plus, plus. Plus. Now, it's not going to be this electron that it's emitted, this beta particle, because it's so fast, it's already left the nucleus, it's already gone. And that can cause ionizing radiation. It has a negative charge and it moves really rather quickly. And so now this can go several meters in air. It can go through perhaps a thin sheet of aluminium, maybe a couple of millimeters. So aluminium will stop it. Several meters of air will stop it. But again, this is quite dangerous. Beta particles are quite dangerous to humans or to biological life if you're very close. Because they, even though it doesn't have much mass, an electron only has 1/1837th the mass of a proton or a neutron. Low mass but high speed, so it does still have a lot of momentum, and it has a charge, so it can cause ionization and cellular damage in biological systems. However, it will be scattered and it will lose energy after a couple of meters of air, like in this room. Okay, so beta particles are just very fast electrons which are emitted by the breakdown of a neutron into a proton and an electron and an anti-electron neutrino. For those really sharp of you out there, does it have to be an electron? Can it be a positron, an anti-electron? And the answer is yes. You can get inverse beta decay. And what happens there is, in fact, a proton can break down into a neutron, a positron, and would that break down? Would that become nice? I'm just trying to think of the actual pathway. I have to be electrically balanced. That would be negative. Oh, would be a neutron would be an antiproton. Antiproton. That would be negative. That would be positive. Antiproton, anti-electron. It wouldn't be an anti-neutrino. It would be the correct neutrino. It would just be an electron neutrino. So you can get positrons, positive electrons, also emitted under certain circumstances. Again, to make sure that the nucleus is stable. However, in the simple form, simple beta particle decay transforms a neutron into a proton in the nucleus. The electron gets emitted, as does the anti-electron neutrino, and so you can transform carbon into nitrogen. This is stable. This nucleus is not stable. This nucleus is stable. Now I'm going to leave this up just a little bit longer. Let me get rid of this. I'm going to leave my nitrogen up. Sorry, I couldn't remember the right word there. Leave my nitrogen up. And now we're going to jump to gamma rays. Gamma rays. Okay, now gamma rays, this is a form of traditional radiation. It is a photon. Okay, it's very, very high energy. So for instance, the energy balance goes, let me do it up here. You have gamma rays, gamma, X-rays, UV, visible, infrared, and radio. Radio is very broad. It has a very long tail. This is very high energy. This is very low energy. So high energy, short wavelength, low energy, long wavelength. So gamma rays are really very, very energetic. Now, we don't see them too often on Earth because thankfully we have the Earth's atmosphere shields us from the gamma rays that are emitted by a little bit from our sun, but mostly from very energetic processes, either in the galaxy or in other galaxies. So supernovae going off, emission and absorption of radiation around black holes, for instance. Supernovae, we talked about novae. There's all kinds of reasons why gamma rays are produced. Luckily for us, the vast majority of them from space do not penetrate the Earth's atmosphere, which is really good. So I've left this up deliberately. Gamma, so this is a photon of energy. So just like the lights from these light strips, I've got some illuminating lights here because it's too dark and the camera won't pick it up otherwise. All the sort of photon radiation that we see, like from the sun, for instance, this is all the same thing. They're just photons, but this gamma rays just happen to be very, very high energy, very dangerous, of course. Unless you're the Hulk. The Hulk can take it, we can't. Gamma rays occur when you've had this type of process. You have an isotope, or you have an end result, or like a daughter product. The carbon was transformed into nitrogen, but the nucleus still isn't stable. What then ends up happening is you get these neutrons and protons, and they're in the nucleus, but they're still jostling around. They have far too much energy, and they want to settle into their energy levels. There are energy levels inside the nucleus, just as electrons have energy levels orbiting the nucleus. Well, the nucleus isn't stable, and so it's in trouble. It doesn't know what to do. It's agitated, and so the particles, the protons and neutrons just they're agitated. They don't know what to do. They're trying to get in the lowest possible energy state. Well, one way the nucleus can achieve stability is by emitting a gamma ray, because that takes energy out of the nucleus. So let's say you have a proton in an elevated energy level. It can emit a gamma ray and it can drop down to a lower energy level. And so it becomes more stable. And we can talk this through in perhaps a later episode, but these energy levels are very, very discrete. Electrons do it all the time. It's one of the reasons why we have radiation and photonic radiation, because it's electrons changing energy states. Well, that occurs in the nucleus as well, but the energy levels are much, much closer together. And so what ends up happening is the energy states are in gamma rays. They're not in, say, the visible light. So really, when you have something like this where the protons or neutrons aren't settled, one way for them to become more settled, the nucleus to become stable, is they emit a gamma ray. And so what can happen here is a gamma ray is emitted. Now, gamma rays you've got to be careful. Gamma rays are really dangerous. They will penetrate. They can penetrate not a fairly long way in air, several tens of meters. You need several pieces of metal or aluminium, lead, something like that, to block gamma rays. Several meters of concrete, like if you have concrete sort of like this, because they're highly penetrative. And they're highly penetrative because the wavelength of a gamma ray looks something like this. Squeaky pen. Very, very, very short wavelength, very high energy. And so when it interacts with, say, a biological system, the penetration depth can be quite large because the wavelength is so short. So you need several meters of concrete that will stop gamma rays. Maybe a good couple of tens of centimeters of lead plates or aluminium plates. So you're talking about this much aluminium or lead. And of course, air, they can go quite a long distance. And gamma rays are really dangerous, again, for biological systems because they carry so much energy. They're even have higher energy than X-rays. They can penetrate deep inside biological systems, cause cellular damage, and ultimately for animals and plant life, it can kill you quite quickly. So you've got to be really careful with gamma rays. I have a very nice story where when I was doing my undergraduate degree in London, Imperial College had a research nuclear reactor just outside of London. I can't remember where it was now. I think was it Reading or Bracknell, somewhere like that. Anyway, they had this nuclear reactor. It was all for research. And so what we would do is we would take off beam lines from the reactor. So typically fast neutrons, medium speed neutrons. And we'll talk about those in a second. Now, free neutrons only last about 10 minutes before they decay. And so what we would do is we would take medium speed, fastish neutrons from the reactor, and we would send them down a beam line, and then we would play attenuation games. How much wax did it take to stop a neutron? How much aluminium plates? And so we would put together these little aluminium plates, and we would work out the penetration depths of these neutrons coming off the reactor. Super fun. Well, one of the things that I actually got to look inside the reactor, which was pretty cool, sort of, because I was a physics major and I was really interested, astronomy physics major, but I was also in awe of this radiation. Now, we got to look inside the reactor because it was a water reactor. Now, what that means is the reactor was really at the center of this really large sort of vessel, almost like a big swimming pool, but it was sort of more vertical. And we climbed to the top, and the professor took off the lid of the reactor, and we got to look inside, and there was this beautiful blue glow. It was blue-purple, not quite like my shirt, not quite as purple as this glow, but you will have seen it in movies. You see like the reactor glowing. Well, that's called Cherenkov radiation. And essentially what's happening is you're seeing a phase change as radiation goes from essentially being emitted from the reactor through being changed by the refractive index of water. And the glow is one of the most beautiful things I've ever seen outside the birth of my children. Just phenomenal. Very, very beautiful glow. You almost can't stop looking at it. It's very effervescent. Well, actually, effervescent means to give off gas, not effervescent. It's very, it's sort of, it's odd to describe. It sort of touches, even though I'm a scientist, I was sort of really touched by the humanity of seeing this blue glow, this purple glow from the Cherenkov radiation. And I remember looking at it thinking, oh, I can't take my eyes off this. This is just so beautiful. It's sort of really, this is really why I did physics and astronomy. I wanted these experiences. But after about 5 seconds, I was like, oh, God, I'm looking at a nuclear reactor. I'm looking at the Cherenkov radiation. It's so beautiful. Oh, my God, I'm looking at a nuclear reactor. Close the lid, oh, my God. But of course, the water's there not only to help keep the reactor cool, but also to stop a lot of the more dangerous radiation reaching us. And so the gamma rays could not reach us because there was tens of meters of water protecting us. But still, just the beauty of this blue-purple glow from the Cherenkov radiation as the photons were slowing down or changing their speed as they were going through different refractive phases. Just beautiful, beautiful, beautiful. Okay, well, we were talking, sorry, I digressed a wee bit there. Well, we were talking about neutrons, so let's finish this off. So we did gamma rays, very high energy, so nucleus trying to get settled. So let's finish off with neutrons. Now, again, this can be, and I'm not going to go for any particular element here. I suppose I could do carbon 6, 1, 2, 3, 4, 5, 6, and then some. I am actually not sure. Neutron. 1, 2, 3, 4, 5, 6. I'm just going to give it another one. 7. So this is this must be 13,6 carbon. And we're going to work this out. Carbon 6, 13. 1, 2, 3, 4, 5, 6 protons. So that's the element carbon. The element by definition is the number of protons in the nucleus. 1, 2, 3, 4, 5, 6, 7. 7 plus 6 is 13. That's the total mass number. So again, we've got a slight imbalance. This is an isotope of carbon. There is a carbon 12,6, which is stable. Graphite, diamonds, all that kind of stuff, coal. There's 13,6 carbon and 14,6 carbon, which we just talked about, being able to transform radioactively through beta decay into stable 14,7 nitrogen. Well, one way for 13,6 carbon to become stable, is to emit a neutron. So if a neutron were to be emitted, it would end up becoming 12,6 carbon, which would make it stable. 12,6 carbon is very stable, lasts eons. I mean, there's been carbon in the universe in gas clouds for billions of years. 12,6 carbon is very, very stable. 13,6 carbon is less so. I actually don't know the half-life of these isotopes, but they do decay. And one of the ways it decays is giving off a neutron. And so really, when you just give off a neutron, it's electrically neutral, hence the name neutron, so there's no charge. No charge. Its mass is very similar to that of a proton, just slightly larger actually. And they tend to move relatively slowly. Even the reactor I used when I was at, I used the Imperial College reactor in undergrad. I can't remember the actual speed. I don't think we ever measured the actual speed. But these neutrons, they decay on their own. Just if I had a neutron here, just sitting in my hand, it would decay within 10 minutes. They just break down. They can be stopped really easily by a lump of wax, or even these very thin plates of aluminium. So they actually don't cause cause that much penetration. Now, for human systems, they can cause a fair. That much wax or that much aluminium. If that were to go into your body, that would cause some damage. Now, they don't have a great deal of mass. Of course, they don't have charge. So it doesn't cause that much biological damage to cells. So these are the 4 main radioactive, radiometric radiations that we encounter. For biological systems, they can be really quite dangerous. Obviously, gamma rays, really, really dangerous. Massive amount of cellular damage can be caused. Beta particles, the same thing. The definite damage can be caused. very low mass, but they move very quickly, so the momentum can be quite high, but relatively easily stopped. Alpha particles don't move very quickly, highly charged, +2, because of the 2 protons, and there's 2 neutrons, electrically neutral, but there are 4 particles, 2 neutrons, 2 particles. So that's quite a big molecule to actually enter into, say, a biological system like us. So it can cause a lot of cellular damage. So really, that's why radiation is so bad for you, because the 4 different types of radiation, radiometric radiation, could really cause cellular damage to animals and plants. So this is one of my real favorite topics in physics. Again, radiation of all of the non-photon radiation, of course, well, gamma rays are photons, but this radiometric radiation, we see it everywhere in the universe, actually. It's all over physics. So very, very interesting. Nice story to finish off here. These radium, I was talking about radium with Marie Curie. She really discovered the nature of radioactivity. And as I said, she won 2 Nobel Prizes for it, one of the very few people to have won 2 Nobel Prizes, first woman to win a Nobel Prize. Phenomenal scientist. I've read a little bit of her thesis, actually, which was written in French in 1903, I believe. I'll have to check that. Very early 1900s. Unfortunately, she died very young because she was dealing with radium. And until she did her phenomenal work in understanding radioactivity, we didn't understand how bad and how dangerous radioactivity of this type is for biological systems, especially humans. And she died at a very young age, actually. She developed cancer. And her cookbooks that she used at home, they are kept in a museum in Paris, and they are still to this day so radioactive that they are kept behind leadened glass. So what happened was she would do her research in her laboratory, go home and prepare dinner or bake or do whatever she did with the family, but she had radium on her fingers. And so as she would turn the pages of her cookbook, she left traces of radium and the radioactive elements she had been working with. And so today, 100 years later, 120 odd years later, actually, her cookbook is still so radioactive, it has to be behind shielding. The general public cannot approach it because it's still too radioactive. Just incredible. Very, very fascinating area of physics, but very, very dangerous. Anyway, this has been a real fun topic. Thanks for watching.